Welcome to our deep dive on a really thought-provoking paper. It gets right to the heart of a core trade-off in generative AI, how you train a model versus how you use it. You could almost say it's about training for the absolute worst-case scenario in order to unlock the power to plan for the very best. So here's our plan. We're going to start with the fundamental difference between masked and autoregressive models. Then we'll dig into this idea of training for the worst and how it leads to planning for the best. After that, we'll get into the pretty amazing results, and finally, talk about what this all could mean for the future of AI. Okay, so at the heart of this paper, you've really got a classic engineering trade-off. It's all about two different ways to think about generation: autoregressive models, which we'll call ARMs, and masked diffusion models, or MDMs. Yeah, this table lays out the whole tension perfectly. On one side, you have ARMs. Their training is pretty straightforward, right? They learn to predict the next token in a set order, usually just left to right, like reading a sentence. It's simple to train, but the catch is, when it's time to generate, they are stuck in that exact same rigid order. MDMs? Well, they're the total opposite. Their training is way more complicated because they have to learn to predict any missing token no matter where it is. It's this tough order-agnostic training, but what you buy with all that pain is incredible flexibility when you go to generate.
Exactly. And that really brings us to the first big piece of the paper's argument. If these MDMs have such powerful flexible inference, why do we so often see them struggling on standard benchmarks, especially compared to ARMs? And the answer, as you might guess, is baked into that really complex training.
Precisely. You can think of it like this. An ARM basically learns one job: predict the next word. But an MDM has to learn what feels like an exponential number of jobs. The paper puts it well. It has to learn to predict a token based on any random set of context tokens. That's like asking it to solve every possible fill-in-the-blank problem you could ever imagine, all at once.
Which, of course, leads us to the central question driving this entire research. Is all that flexibility you get at inference time really worth the absolutely brutal training process? It's the classic question of whether the ends actually justify the means.
And this chart from the paper just puts the problem in really stark empirical terms. What you're looking at is model performance plotted against the amount of compute you throw at it. The orange line way up top, that's the autoregressive model. It learns the most efficiently. And you can see this clear trend as you move away from that clean left-to-right order, from the ARM to a random order model, down to the full any order MDM in blue. The performance just gets worse and worse for the same amount of compute. It's pretty clear proof that a lot of the subproblems an MDM is forced to learn are just fundamentally harder.
So, okay, we've established it. The training is demonstrably harder, no question. But that's really only half the story here. The other half, the optimistic part of the paper, argues that the MDM's greatest strength, that incredible inference flexibility, can actually be used to completely sidestep its biggest weakness.
Exactly. And this is where it gets really clever. The key insight is that the model can be strategic at inference time. Look, during its brutal training, it was forced to learn how to solve both easy and hard prediction problems. But when it's actually generating something, it doesn't have to just randomly pick a token to fill in. It can look at all the blank spaces and deliberately choose the one it feels most confident about. It gets to plan for the best, easiest path forward.
So how does it do that? Well, the paper proposes two really simple but powerful strategies. The first one is top probability. It's super intuitive. Just find the blank spot where the model is most certain about what the single answer is. But the second one, top probability margin, is a bit more subtle, and it turns out way more effective. It doesn't just look for the highest probability, it looks for the biggest gap between the number 1 and number 2 predictions. This is a much better way of measuring true certainty because it avoids those tricky spots where the model is kind of torn between two pretty good answers.
And what's so wild about this is that you can completely change the model's behavior without any retraining at all. It's just about being smarter at inference time. To prove this, the authors chose the perfect test case, logic puzzles, specifically Sudoku, where there is no single natural left-to-right way to solve it. You have to be strategic.
And well, the results in this table are pretty remarkable. Look at the standard MDM with only 6 million parameters using random unmasking. It's a total failure. It solves less than 7% of the puzzles. But that exact same model, just by switching to the top probability margin strategy, suddenly jumps to almost 90% accuracy. And get this, it actually beats a much, much larger 42 million parameter ARM that was spoon-fed the correct solution order during its training.
Right? Let's just sit with that number for a second.
89.49%. This isn't just some small incremental improvement. This is a total game changer. A model that was basically useless becomes a world-class Sudoku solver, not through more training, but just by changing how it decides what to think about next.
And this really gets at the deeper implication. That ARM model was essentially given the answer key during its supervised training, but the adaptive MDM, it figured out the optimal path to the solution all by itself, on the fly, during inference. It's a pretty stunning case of an unsupervised inference method just crushing a supervised training one.
And this advantage holds up even when things get harder. This next table shows what happens on a set of tough Sudoku puzzles the models had never seen before. The big ARM's performance just craters, dropping down to about 32%. But the little adaptive MDM is way more robust. It's still solving nearly half the puzzles, which really suggests that its difficult, messing training gave it a much more generalized understanding of logic.
Okay, so let's zoom out. What does all of this really mean for how we build generative AI models in the future? Because these findings really do seem to point towards some pretty exciting new ways of thinking.
I think the key takeaways are pretty clear. First, for any task that doesn't have a single obvious generation order, think complex reasoning, planning, stuff like that, MDMs with this adaptive approach could be incredibly powerful. It also shows us that inference strategy is this massive, maybe underexplored tool we have for boosting performance. And finally, it completely reframes that complex MDM training. It's not a bug, it's a feature. Training for the worst builds this really robust foundation that allows for planning for the best. Now, of course, we have to remember these incredible results were on very structured logic puzzles. It's still an open question how well this works for more open-ended things like creative writing.
And that really leaves us with this final, massive question. For so long, we've kind of assumed that generation has to be a fixed, linear process. But this research shows it can be a dynamic, strategic choice. So if a model can actually decide the most logical path to building an answer, what new kinds of complex reasoning and planning does that suddenly unlock? It really points to a future where models don't just follow a pre-written script, but can actually chart their own course to a solution.